So one last little concept that we're going to talk about introduces us to the concept of material strength and how strong materials are. We mentioned, for example, airplanes. The material they're made of need to withstand the pressure difference. Inside the airplane you have 1 atm to make it comfortable for people to breathe. Outside the airplane you have less than 1 atm because you're at such a high altitude. So the materials themselves that the plane is made of needs to be able to withstand those pressure differences. So we talk a bit about how strong materials are. When you are dealing with materials and looking at how they behave, we have what's called a stress-strain curve. Meaning we're plotting stress on one side and strain on the other. The stress is a measure of how much pressure your object can withstand, or how much pressure is just being applied to it. The strain is a measure of how much your object deforms. Turns out, materials, at least for a certain region, the relationship between the stress and the strain is a linear one. For a certain amount of stress, there's a certain amount of strain, and it changes linearly within a given region. At a specific point, we reach what's called the yield point. From that point on, the material will no longer be linear. What that means is you've basically permanently deformed it. As long as you stay in this linear region, your object is not permanently deformed. For example, a rubber band. If I stretch a rubber band out and let go, it goes back to its original shape. That's this region here. We call this the elastic region. Because an object, as long as you stay in that linear region, the relationship between the stress and strain will always be linear, and your object will be able to go back to its original shape. Once you reach what's called the yield point, you will now have permanently deformed the object. It will no longer go back to its original shape. Good examples of slinky. I imagine all of us at some point have played with a slinky, and it was so easy to ruin that darn thing. You can get kinks in it. That's the yield point. You get those kinks. Okay? It's no longer linear after that. It can't go back to its original shape. There is also a breaking point where the object actually physically breaks. That happens at a certain stress. What we're going to talk about is the slope of this line. The slope of this line is called the elastic modulus. So the slope of the linear region is called the elastic modulus. All materials have a specific elastic modulus. The elastic modulus is the ratio of stress over strain. The pressure is applied over the deformation of your object. So for example, a rubber band. A rubber band would have a very, very shallow slope. Why? Stretches really easy. It doesn't take a whole lot of forces to make it deform by a lot. So a rubber band is really shallow. Something like steel, if you have a big old steel beam, bone in your legs, in your arms, it has very steep lines. That means it requires very, very large forces to deform them by just a little bit. Okay? But at any rate, the slope, regardless of whether it's steep or shallow, is the elastic modulus. There's two moduli we're going to talk about. One is called Young's modulus. Young's modulus is specific to stretching or compressing along just a single line. So that would work for a rubber band. It would work for, say, a steel beam as long as you're just pushing in on it or pulling out on it. Young's modulus, your book uses a capital Y to represent it. The stress is calculated by force over area. So for example, if we had a steel rod, the force, whether we're pulling out or pulling in, the force is whatever force is applied. The area is the cross-sectional area here that is applied over. So if you were to cut the rod and look at it, the end, you'd see the circular end. It would be the cross-sectional area of that circular end. So that's the stress. The strain is the measure of the deformation. The strain is the change in length of your rod over the original length of your rod. So as you stretch and pull on that steel rod, you're going to have to pull and stretch awfully hard to have any sort of change in length. But as you pull or stretch on it, its length is going to change. With steel, it's not going to change by much, but it will change. So the strain is the ratio of how much the length changes by over the total length, the original length of the object. Okay? Now units. Delta L over L naught, the units of meters are going to cancel. So strain is actually unitless. It has no units associated with it. Stress is newtons per meter squared. So Young's modulus has units of newtons per meter squared over nothing. So units of Young's modulus are newtons per meter squared. You don't generally see it written as pascals, though. Even though we know a newton per meter squared is pascals, we tend to leave it as newtons per meter squared. Okay. Now, there are multiple types of moduli. Our book only talks about two. Young's modulus is specifically just along a line. You're stretching or compressing along a single line. The second modulus our book talks about is the bulk modulus. That is, if you have forces in all directions, so basically a pressure from every direction acting on your object. Your book uses a capital B to represent it. So the stress is simply the change in pressure. Whatever additional pressure you apply, or the less pressure you apply, however much you've changed the pressure by. The strain, if you've got forces coming from all directions, your dimensions are going to change in all directions. So your overall change in size is going to be a change in volume over the original volume. But we need one more piece of information here. If I have all these pressures pushing in, these forces pushing in, so an increase in pressure, what's going to happen to the volume of this object? It's going to get smaller. So an increase in pressure always corresponds to a decrease in volume, and vice versa. We don't want negative values for B, so we need to put a negative sign in the equation, because delta P and delta V will always have opposite signs. As pressure gets bigger, delta V will get smaller. But again, delta V over V naught, meters cubed over meters cubed, strain still has no units. Pressure, still newtons per meter squared. So the units, regardless of the type of modulus it is, the units are newtons per meter squared. Every material is going to have what we call a yield strength. Your book doesn't talk about yield strength, that I remember anyway. Yield strength is basically the maximum stress you can apply before you've permanently deformed your object. There's a certain maximum stress you can apply to a material before it's permanently deformed. And then the breaking point is the maximum stress to break it. Break your object. So materials, this is something that needs to be taken into consideration. If you're building an elevator, for example, you have certain forces that you know are going to be applied. You plan for a maximum amount of force. Well, you need to make sure that you have the correct size cables in there that can withstand the forces that are going to be applied. They usually use what's called a safety factor. So if you know you're going to reach 1,000 newtons, you're not really going to plan for 1,000 newtons and use the minimum value of area you can possibly use, because then you're running the risk of breaking it. Use a safety factor, for example, of 10. That would mean you're going to really plan for a maximum of 10,000 newtons. So you're going to plan for 10 times more and build it to specs for that, and then when you actually say your maximum occupant load is up to, say, 1,000, then you hopefully, when people don't read the signs, won't exceed it. Okay? Yes, exactly. Design, intuit, user error.